Today I'm going to be teaching a little bit more about calorimetry, which is the science of heat exchange. So we naturally know that in nature, when you have a hot body and a cooler body, heat will spontaneously flow from the hot to the cold until the two bodies reach a state of thermal equilibrium. And thermal equilibrium exists when the two bodies have equal thermodynamic temperature. So calorimetry is the study by which systems exchange heat. So let's just look at the example for a moment of water. Now imagine I have some ice, and we know that I'm going to make a plot here for water, H2O, and imagine that the temperature is on the vertical axis, and then on the horizontal axis I'm going to use the symbol Q, and Q represents the cumulative heat added. All right, now let's look at some important temperatures for water. First of all, we know that 0 degrees Celsius is the freezing point, 100 degrees Celsius is the boiling point at standard pressure and temperature. So then let's imagine we start off with ice. And as I've indicated there on that little blue line, that ice temperature, that looks to be roughly, negative 10, negative 20 degrees. I'll say that this is the temperature of the ice. Okay, now I'm going to have to, this ice is in solid phase, and if I start to add heat to it, the ice will warm up until it reaches 0 degrees. So solid until it reaches 0 degrees. Now, how much heat does it take to warm the ice up? What's this amount of heat right here? Well, this amount of heat, Q, is equal to mass times a quantity we call the specific heat of ice times delta T, final temperature of the ice minus the initial temperature of the ice. So the specific heat of ice is a quantity that measures the ability of solid water to store energy. So specific heat is the amount of energy it takes to change a certain amount of mass of ice by a certain number of degrees Celsius. And there is some microscopic physics that goes into actually calculating this quantity. We're just going to take the experimental numbers for this, but basically it measures the ability of the water to store energy in microscopic degrees of freedom. So the specific heat of ice is equal to 2090 joules per kilogram Kelvin. So this means it takes just over 2,000 joules of energy to change 1 kilogram of ice by a single Kelvin. Now, just to put this in context a little bit, let me remind you that calorimetry, its calorie has to do with energy or heat energy, and meter studying the flow of, or way of tracking the flow of energy. So 1 calorie is equal to 4.19 joules. However, a food calorie is normally given a capital C, and that is actually a kilocalorie. So that would be 4,190 joules. All right, so this is how much energy it takes. This is the ability of ice to store energy in its internal degrees of freedom, but it still remains solid ice. If I continue adding heat to the ice, well, at 0 degrees is where it begins to melt. And when it's melting, there's a certain amount of energy it takes to melt the ice. And this amount of energy we call latent heat. So this is the amount of energy it actually takes to break the molecular bonds between water molecules that hold them together, and now they can freely slide past one another. So this amount of heat here, Q, is called the latent heat of fusion. So if I want to melt a certain amount of ice, the latent heat of fusion is a quantity which tells us how much energy it takes to actually tear water molecules apart from each other and let them slide freely past one another as they do in a liquid. So this is experimentally comes out to 333,000 joules per kilogram. So this is, you can see, much larger than the specific heat, or just the number of joules is much larger. And this would show you how, in one sense, how tough these molecules really stick to one another. All right. Okay. So continuing on here now, let's see. Well, once the ice has undergone a phase transition, it's all melted at 0 degrees. So during this part of the curve, the ice undergoes a phase transition to liquid water at 0 degrees Celsius. It can coexist at the same temperature. And then now that liquid begins to warm up if I continue to add, or if I cumulatively add heat. Right, and it's going to keep heating up. It's going to stay liquid all the way until it reaches 100 degrees Celsius. And once it reaches 100 degrees Celsius, this is when it begins to boil. And it boils at 100 degrees Celsius until it's all boiled away and it becomes a gas. And at this point, afterwards, we have a gas. All right, so let's look at some of these quantities here now that remain. So what's the amount of heat taken to warm up the water? Well, this Q just equals mc water delta T. Now, interestingly enough, the specific heat of water is different than that for ice. In fact, it's about twice. So it's 4,190 joules per kilogram Kelvin. Why might it be about twice? Well, in one sense, you can think of water. It has more internal degrees of freedom. The H2O molecules are not rigidly locked in a crystal structure, but they can freely move about and rotate and slide past one another. So the energy that you input can be stored in more ways. So it takes more energy to increase the overall thermal energy, and thereby the temperature of the system. We'd say it has a higher. H2O has a higher thermal inertia, I would say, when it's in the liquid phase versus when it's in the frozen phase. Okay, so that's this temperature right here. Now, what about boiling? Well, this is another phase transition, so this is going to require another latent heat. And this is called the latent heat, not of fusion, but the latent heat of vaporization. All right, and then finally, what about when we're in the gaseous phase? Right over here, how much heat does it take? Well, now we have a specific heat due in the gas phase, and this can come in different forms because there's different ways to add heat to a gas. You can do it at constant volume, in which case I have a specific heat at constant volume, or you can do it at constant pressure. Where N is the number of moles and the subscript P denotes constant pressure. So it depends on the process when you're in the gaseous phase. All right, now I want to combine this with the first law of thermodynamics. Which is really just a statement of energy conservation. And what this says is Q plus W equals delta E thermal. So if I want to change the thermal energy of a system, in this case my system is water, I either do work on the water or I add heat to it. Now we're going to be dealing with frozen and liquid water, in which case this work is equal to 0. It's pretty much 0 for liquids. Most liquids are very nearly incompressible. So remember, heat, or Q, sometimes we call this heat, is a thermal transfer of energy, whereas work is a mechanical transfer of energy. And since you can't compress a fluid, specifically water, it's nearly incompressible, there's no work done on a fluid. All right, now let's apply this to a simple system where we study some heat exchange. And I'm going to look at simply just mixing ice and water together. So let me say I have ice and water. And what I have here is a cup. And inside this cup is water. And inside the water there's a bunch of cubes of ice. So here's the ice. And then everything that surrounds the ice is the water. Okay, now we could ask the question, if for a given amount of ice placed inside this beaker, which is called the calorimeter, with a given amount of water, the system's going to reach an equilibrium temperature. The first thing that's going to happen is the water molecules start to bombard the ice and kind of are vibrating it, and that causes a transfer of energy into the ice, causes some of those ice molecules to be liberated. They start kind of jiggling faster and faster. Now, depending on how much ice and how much water you have and their temperatures, you may melt all of the ice and go directly to the liquid and everything becomes a liquid phase, or you might have so much ice that the temperature of the water goes down to 0 degrees and there's some ice remaining afterwards. So you're going to, when thinking about calorimetry problems, you have to first of all think about, well, is there enough energy in the water to melt all the ice? If there is, then the system will come to equilibrium at some temperature above 0 degrees. If there's not, then the temperature of equilibrium will be 0 degrees. And that will determine how we set up our calorimetry equation. So right now this is just a cup, but if I try to construct a calorimeter, I want I want as little heat as possible to be escaping. So I'm going to put a lid on here. This is for some thermal isolation. And then let me also put a insulating cup around it. This also serves as thermal isolation because I don't want heat to escape from the mixture of the water and the ice to escape into the environment, because that will change my equilibrium equation. So what we're waiting for here is the system to come to equilibrium. Right, now, if the water is very cold, it's going to take a long time for the system to reach equilibrium, and even with very good insulation, you're going to get a good amount of heat that escapes. But if the water is really hot, the system will come to equilibrium much quicker, and this then allows for less heat escape from your system. So the purpose of doing a calorimetry type experiment such as this is this gives us a way to actually measure the latent heat of fusion. And that's what we're going to try to measure here directly. Other things that we can measure when we do calorimetry is, the specific heat of ice, specific heat of water. Calorimetry gives us a way to measure specific heat. So let's say that this cup right here is made out of aluminum. Well, if it's made out of aluminum, aluminum is going to have a specific heat as well. So let's write down the relevant quantities here. Specific heat of aluminum, let's say we know what it is, 900 joules per kilogram Kelvin. Okay, so when the system comes to equilibrium, that basically means there's a heat exchange that's going on between the ice and the water, and there's a heat exchange going on between the aluminum and the water, and in a short amount of time, in a certain amount of time, the system no longer is exchanging heat. That's when it's reached equilibrium. So what we could write then for our calorimetry equation is we could write the heat lost by the water plus the heat lost by the aluminum plus the heat exchanged by the ice has to equal 0. Now, if these numbers all sum to 0, this Q for each case is just the heat exchanged. You know that at least one of them has to be negative. Maybe two of them could be negative. But if the ice is colder than the water and the aluminum, let's see, the water and the aluminum are both going to lose heat because their temperatures are going to decrease, and the ice is going to gain heat, either by melting some of the ice or by melting all of it and beginning to warm it up right here. All right, so then all we need to do, since we want to solve for the latent heat of fusion, is we need to simply plug in what each of these quantities is going to equal. So for water, mass of the water plus the specific heat of the water plus the change in temperature of the water. This is going to have to be known. Let's say we know the mass of the water, we know the specific heat of the water, and we just measure the final equilibrium temperature. we need to know the equilibrium temperature. That's something we can easily measure. And really, I shouldn't write measure LF. It's indirectly measuring. We're really calculating the latent heat of fusion, but we're measuring the equilibrium temperature, given that we know, the mass of the water, the mass of the ice, the mass of the aluminum cup, and the specific heats of each of these. We can just solve for our one unknown by setting up our calorimetry equation. So here I have the first term. The second term for the aluminum would be mass of the aluminum plus the specific heat of the aluminum times the change in temperature of the aluminum. The aluminum should have the same change in temperature as the water if it was in equilibrium with the water before the ice was added. Then I have the terms for the ice, and there's actually going to be potentially 3 terms for the ice. The first is the mass of the ice times the specific heat of the ice times the final temperature of the ice. Let's just consider the case where there is enough water at a high enough temperature to melt all the ice and warm it. So first of all, in order to reach equilibrium, first thing you need to do is you need to melt the ice. So the change in temperature is 0 minus the initial temperature of the ice. The next thing you need to do, so this term right here, it warms the ice to 0 degrees. The next thing you need to do is actually melt the ice. And the final thing you need to do is warm the melted ice to the new equilibrium temperature, which the system comes to, and that's what can be measured very simply in a calorimeter. So the ice really has to undergo 3 parts of this curve. It has to, first of all, be warmed to 0 degrees. This takes a certain amount of energy. Then it has to melt or undergo a phase transition to become liquid. And then that liquid is going to be warmed up to whatever temperature it can be, depending on how much water is available and what temperature it's at. So all of this together equals 0. Now the idea here is everything in this equation is known or easily experimentally measured. The only thing that's unknown is the latent heat of fusion right here. So I solve for the latent heat of fusion, and then I'm going to take the number that I get and I'm going to compare it with the standard known value to see how well my experiment worked out. So you can do this with a number of different substances. You could, for instance, mix a hot copper block in a cold. Instead of putting ice cubes in here, you could put hot copper in the water. And you could measure the equilibrium temperature, and that could allow you to determine the specific heat of copper. You could do the same thing with aluminum. There's a number of different... So typically what calorimetry is used for is to determine this value right here, the specific heat of some unknown quantity. It can also be used to determine the latent heat of a particular substance as well, if it's undergoing a phase transition. Now this is very important, of course. It's important to know the thermal properties of materials, especially water, because water is one of the most important substances when it comes to sustaining life. So it's very important to know how water stores energy, and we can even think of our Earth being covered with a lot of water, and it's important to understand how that ice stores energy that's input externally.